Hello and welcome to Earthly Teachings, where learning is clear and powerful. Today, we're working on Mathematics N6. Let's learn together. In this video, we'll tackle question 4 from your N6 syllabus. This question covers two fundamental topics in differential equations. Our objectives for this lesson are twofold. First, we will learn how to solve a first-order linear differential equation to find a particular solution. Second, we will learn how to solve a second-order linear non-homogeneous differential equation. These two types of problems are very common, so mastering them will greatly help you in your exams. We'll go through each step carefully, explaining the why behind everything we do. Let's start with our first problem. Question 4.1 asks us to determine the particular solution of x times di sin x equals y plus x squared times sin of x, given the initial condition that y of pi equals 0. Before we can solve this, we need to identify what type of differential equation it is. Notice that we have y and dx. This tells us it's a first-order equation. And it involves y and its derivative in a linear way, which suggests it might be a linear differential equation. To confirm this, we must put it into the standard form for a first-order linear differential equation. The standard form is di/dx plus p of x times y equals q of x. Our first goal is to rearrange the given equation to match this form. Let's begin with our equation. X times dx equals y plus x squared sin of x. The first thing we need is for the dx term to have a coefficient of 1. Right now, it's x. So we'll divide the entire equation by x. This gives us di/dx equals y over x plus x times sin of x. We're one step closer. Now we need the term involving y on the left side with the di/dx. We can do this by subtracting y over x from both sides. And there we have it. This equation is now in the standard form di(x plus pxy equals qx. By comparing our equation with the standard form, we can clearly see that p of x is 1 over x, and q of x is x sin of x. Identifying these correctly is the first critical step. Now that our equation is in the correct form, our next goal is to find what we call the integrating factor. This is a key tool for solving linear first-order differential equations. The formula for the integrating factor, which we'll call IF, is e raised to the power of the integral of p of x dx. Why do we use this? The integrating factor acts like a magic key. When we multiply our differential equation by it, the entire left side becomes the derivative of a product, the integrating factor times y. This makes the equation easy to integrate. Let's calculate our integrating factor. Remember, p of x is 1 over x, so we need to calculate e to the power of the integral of 1 over x dx. The integral of 1 over x is negative the natural logarithm of x, or ln x. Now we use a property of logarithms. Remember that a coefficient in front of a logarithm can be moved inside as an exponent. So, x becomes ln x to the power of 1. This is the same as the natural logarithm of 1 over x. Substituting this back, our integrating factor is e to the power of ln 1x. And another crucial property is that e and the natural logarithm ln are inverse operations. They cancel each other out. This leaves us with our integrating factor, 1 over x. It's often helpful to keep this simple fraction as it is. We have now found our key to solving the equation. We're making great progress. We've rearranged the equation and found the integrating factor. Now let's use it. Here's our standard form equation and our integrating factor, 1 over x. The next step is to multiply the entire differential equation by the integrating factor. Let's do that. We multiply each term on both sides by 1 over x. Notice that on the left side, the second term becomes 1 over x squared times y. And here's where the magic happens. The left side of this equation is not random. It's the exact result of the product rule for differentiation, applied to the integrating factor times y. Specifically, it's the derivative of the quantity 1 over x times y. We can verify this with the product rule. The first term, 1 over x, times the derivative of the second dx, plus the derivative of the first, 1 over x squared, times the second term. As you can see, this matches the left side of our multiplied equation perfectly. So we can replace the entire left side with this derivative notation. Our new equation is the derivative of 1 over x times y, all equal to sin of x. This form is incredibly easy to solve. All we have to do is integrate both sides with respect to x. Integration is the opposite of differentiation, so it will undo the derivative on the left. Integrating the left side just leaves us with 1 over xy. Integrating the right side, sin x, gives us cos x. Don't forget the constant of integration c. It's a common mistake to leave it out, but it's essential for a general solution. So our equation becomes 1 over xy equals cos x plus c. To solve for y, we just multiply by x. This gives us y equals negative x times cos plus c times c. This is the general solution to our differential equation. We found a general formula for all solutions to the equation, but the question asked for a particular solution. To find a particular solution, we need to use the initial condition provided in the question. A general solution has a constant, c. A particular solution has a specific value for that constant. The initial condition is y of pi equals 0. This means that when x is equal to pi, y is equal to 0. Our job is now to substitute x equals pi and y equals 0 into our general solution and solve for c. Let's substitute. We get u equals negative pi times cos of pi plus c times pi. Now we need to evaluate cos of pi. You can think of the unit circle, or just recall the graph of the cosine function. At x equals pi, the cosine value is 1. So our equation becomes 0 equals negative pi times 1 plus c pi. This simplifies to 0 equals pi plus c pi. Factoring out pi, we have 0 equals pi times 1 plus c. Since pi is not 0, the only way this equation can be true is if the other factor, 1 plus c, is equal to 0. So 1 plus c equals 0, which means c must be 1. We have now found the specific value for our constant of integration. The final step is to substitute this value of c back into our general solution to get the particular solution. We replace c with 1. This gives us our final answer, y equals negative x equals x minus x. This is the particular solution that satisfies the given differential equation and initial condition. Let's quickly recap our process for a first-order linear differential equation. 1. Rearrange to standard form d plus dl plus p pxy geld cos. 2. Find the integrating factor if e pas e pa dik. 3. Multiply the standard form by the if to get bas d dex ef e equal qx ef. 4. Integrate both sides to find the general solution. And 5. Use the initial condition to find the particular solution. Excellent. Now let's move on to the second part of the question, which involves a different type of differential equation. Question 4.2 asks for the general solution of the second-order non-homogeneous differential equation. d squared y by dx squareds minus 4 times di by dx plus 5y equals e to the power of negative x. How is this different? First, it's second order, because it has a second derivative, d squared y by dx squared. Second, it's non-homogeneous, because the right-hand side is not 0. It's a function of x e to the negative x. To solve non-homogeneous equations, we use a two-step approach. The general solution y is the sum of two parts. It's the complementary solution, yc, plus the particular solution, yp. The complementary solution, yu, is found by ignoring the right-hand side and solving the associated homogeneous equation. The particular solution, yp, accounts for the non-homogeneous part and has the same form as the right-hand side. Our first step is to find the complementary solution, you see. To do this, we set the right-hand side of our original equation to 0. This gives us the associated homogeneous equation, d squared y by d dx squared minus 4di by dx plus 5y equals 0. To solve homogeneous linear differential equations with constant coefficients, we use a technique called the characteristic equation. We propose a solution of the form y equals e to the power of rx. We substitute this into the homogeneous equation. The second derivative becomes r squared times e to the rx, and the first derivative becomes r times e to the rx. Substituting these into the equation, we get r squared e to the rx minus 4re to the rx plus 5e to the rx equals 0. Since e to the rx is never 0, we can divide the entire equation by it. This leaves us with the characteristic equation, r squared minus 4r plus 5 equals 0. Notice how the powers of r correspond to the orders of the derivatives. R squared for the second derivative, r for the first, and the constant for the y term. This is a powerful shortcut. Now we just need to solve this quadratic equation for r. Let's use the quadratic formula. The quadratic formula is r equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our case, a is 1, b is 4, and c is 5. Substituting these values, we get r equals negative 4, which is 4, plus or minus the square root of 4 squared minus 4 times 1 times 5 all over 2. This simplifies to r equals 4 plus or minus the square root of 16 minus 20, which is 4, all divided by 2. So r equals 4 plus or minus the square root of 4, all divided by 2. The square root of negative 4 is 2i. So our roots are r equals 4 plus or minus 2i divided by 2. This simplifies to r equals 2 plus or minus I. We have found a pair of complex conjugate roots. There are 3 types of roots you can find for a characteristic equation: real and distinct, real and repeated, or complex conjugates. Each type has a specific form for the complementary solution. For complex conjugate roots, r equals alpha plus or minus beta I. The complementary solution is y equals e to the power of alpha x times a cos beta x plus b sin beta x. This form guarantees a real-valued solution, which is what we need. In our case, alpha is 2 and beta is 1. So our complementary solution is e to the power of 2x times the quantity a cos x plus b sin x. Remember, a and b are arbitrary constants. We've completed the first step and found the complementary solution. Now for the second step, finding the particular solution. P. The particular solution is a solution to the full non-homogeneous equation. To find it, we use the method of undetermined coefficients. The method involves guessing a form for yp that looks like the right-hand side of our equation, which is e to the power of negative x. We guess yp equals some constant c times e to the power of negative x. Let's call our constant k to avoid confusion with the c from the solution memo. A common trap here is to forget to check if your guess is already part of the complementary solution. Yike! If it is, you must multiply your guess by x. Let's check. Our guess is ke to the negative x. Our yc is e to the 2x times a cos x plus b sin x. Clearly, ke to the negative x is not the same form as any part of yc, so our guess is perfectly valid. Now we substitute our guess for yp and its derivatives into the original non-homogeneous equation. First, we need the derivatives. The first derivative of yt is negative ke to the negative x. The second derivative is ke to the negative x. Now we substitute these into our full differential equation. This gives us ke to the negative x, minus 4 times negative ke to the negative x, plus 5 times ke to the negative x equals e to the negative x. Let's simplify this expression. We have ke to the negative x plus 4ke to the negative x plus 5ke to the negative x, all equal to e to the negative x. Combining the terms on the left side, we get 10ke to the negative x equals e to the negative x. To solve for k, we can divide both sides by e to the negative x. This gives us 10k equals 1, which means k equals 110. We have found the coefficient for our particular solution. Therefore, our particular solution is yp equals 1 over 10 times e to the power of negative x. We now have both parts of our general solution. We've reached the final step. We have the complementary solution, yc, and the particular solution, yp. Remember, our general solution is the sum of these two parts, equals yc plus yp. Our complementary solution was yc equals e to the 2x times a cos x plus b sin x, and our particular solution was y topped equals 1 over 10 times e to the negative x. All we need to do now is combine them to form our final answer. The general solution is y equals e, to the 2x times the quantity a cos x plus b sin x plus 1 over 10 times e to the power of negative x. This solution includes two arbitrary constants, a and b, which is characteristic of a second-order general solution. If an initial condition were provided, we could find their specific values, just like we did in part 4.1. Let's do a quick comparison with the memo provided. In the memo, the constant for the particular solution is labeled c and is found to be 1 over 10. Our solution matches perfectly, with k in our case being 1 over 10. Let's quickly review the exam strategy for these types of questions. The key is to organize your work clearly, step by step. First, identify the type of equation. Is it first-order linear, second-order homogeneous, or second-order non-homogeneous? Each type has a specific solution method. Second, write down the relevant formulas. This shows the examiner you know the process, even if you make a calculation error. Third, break the problem down into manageable parts. For non-homogeneous equations, solve for yc and yp separately, then combine them. This makes the problem less daunting. Fourth, check your work. For example, you can take your final solution for 4.2, find its first and second derivatives, and substitute them back into the original equation to ensure the left side equals the right. Let's perform a quick check for our yp solution in 4.2. We found yp equals 1 over 10e to the negative x. If we take its derivatives and plug them back into the original equation, we should get e to the negative x. As you can see, it checks out. This gives you confidence that your work is correct. Finally, practice is essential. The more you work through these problems, the more familiar you will become with the patterns and methods. Thank you for watching and learning with Earthly Teachings. Like, subscribe, and continue learning with Earthly Teachings. See you next time.